Okay, hi everyone. Welcome to the International Methods Colloquium. My name is Justin Essery. I'm an associate professor of politics here at Wake Forest University. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by Rice University and the National Science Foundation. This week's speaker is Winston Chou, a PhD candidate at Princeton University. I apologize for butchering his name last week, and on behalf of all Americans for butchering everyone's name at all times. His talk is entitled Lying on Surveys, Methods for List Experiments with Direct Questioning. Winston's talk will last about 30 to 40 minutes, after which point we'll take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And you can ask a question at any time, but I'm going to hold all the questions till the end of the talk. So you can ask at any time, but it'll be answered at the end. A link to Winston's slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I will post that link right after we get started with the talk. And now I'd like to welcome Winston Chou to the IMC. Winston, welcome.
Great, thanks very much, Justin. So like Justin said, the title of my paper is Lying on Surveys. And the work that I'm going to present today is a contribution to a very large and vibrant literature on that tries to develop survey tools and methodologies for asking and eliciting truthful responses to sensitive questions on surveys. And so just as a kind of a rough definition of what I mean by sensitive questions, these are questions that attempt to elicit traits, attitudes, and behaviors whose revelation poses some type of risk or is potentially harmful to respondents. So these could include topics like unpopular opinions or uncomfortable facts. So a classic example is, did you vote? Who did you vote for? It includes kind of intrinsically sensitive information, like information on an individual's health or incarceration history, their experiences with the law. And they even span support for armed combatants in wartime. So a large number of these, surprisingly large number of these techniques have been applied in actual conflict zones where you can imagine direct questioning isn't even feasible, let alone reliable or likely to yield good results. So it's not hard to understand at an intuitive level why direct questioning can be unreliable for questions like, do you support the Taliban, or who did you vote for, etc. And as social scientists, we can come up with a lot of domain-specific hypotheses. So in the first example, like do you support the Taliban, it's obvious there's a fear of retaliation there. In the example of do you try to vote, there are social norms and expectations. Or more generally, a kind of desire to project a certain identity to the enumerator or the researcher, or to other people in general. But taking kind of more of a methodological perspective or a bird's eye view, the kind of problem with direct questioning is that it affords response with very little privacy or kind of plausible deniability with regard to whether they have the sensitive trait or not. So this includes both, at the point of collection. So survey respondents might kind of justifiably worry about being judged by enumerators or triggering a set of increasingly invasive follow-up questions, or even kind of post hoc. So after the survey, they might worry about leaving back a record of their response that directly identifies whether they have a sensitive trait or not. So in the event of anonymization. So this is just a schematic. There's this kind of identifiability issue under direct questioning that inhibits truth telling. That leads respondents to kind of obscure whether they have the sensitive trait or not. And this is just also to introduce a notation that I'll use for the remainder of the talk. So ZI star is a latent binary indicator that denotes whether someone has a sensitive trait or not. So whether they voted, so that would be ZI star equals 0, or failed to turn out to vote, or whether they support the Taliban, etc. And the direct response is, the observed response to a question like, do you have the sensitive trait or not? So the kind of shortcomings of direct questioning motivate this large literature and set of techniques, creatively titled indirect questioning. And so these are techniques that seek to break this one-to-one mapping by deliberately corrupting the signal that researchers get from respondents. So the idea here is to increase the variance and the uncertainty of any one particular individual's response in an effort to afford respondents with greater privacy, so as to hopefully encourage them to provide truthful answers and thereby reduce bias in the aggregate. So for any particular individual, we're not sure whether they're providing us with an honest signal of whether they have a sensitive trait or not, but the hope is that we can recover a more accurate estimate of the true population prevalence of the sensitive trait on the back end. So to kind of make this a little bit more concrete, I'm just going to give an example of a very early indirect questioning technique. And this directly obscures individual responses with random noise, again, in this effort to try to increase respondent privacy and thereby elicit more honest answers. So in the randomized response technique, the respondent uses a randomization device, for example, a quarter or a coin, whose distribution is already known ahead of the time to the numerator, but whose particular realization, so any kind of given realization, is not known to the enumerator or researcher. So, for example, in the randomized response technique, they might get, a respondent might get this script that reads, flip this coin, but do not tell me whether it landed heads or tails. If it landed heads, please answer the following question truthfully. If it landed tails, please say yes. And then the question is, many people failed to vote for one reason or another. What about you? Did you fail to vote? So here, the sensitive trait being elicited is, again, the failure to vote. And hopefully people already have this kind of intuitive understanding of how this technique tries to increase respondent privacy. So the basic idea is that instead of the observed response, so in this case here it's y, mapping directly onto the sensitive trait, so conditional on yi equals 0, we know that the respondent flipped a heads and actually turned out to vote, so zi star equals 0. But conditional on observing a 1, we're not sure whether that respondent just happened to flip tails, and so it's giving a forced yes, or if they actually flipped a heads and are answering truthfully, that they failed to turn out to vote. So there's this privacy dynamic that's not present in the direct questioning scenario. And then, again, the hope is that we can identify the population prevalence, so that's expectation of zi star on the back end, and we can easily do that using maximum likelihood. So just to walk through this likelihood function. So conditional on observing the yi equals 1, so a response of yes, it could be that either they flipped a heads and failed to turn out to vote, so that's 1/2 times pi, or they flipped the tails, and that's 1/2. And if we observe a response of 0, then it's the case that they flipped a heads and actually turned out to vote. So that's the randomized response technique. And now I'll pivot to the list experiment, which is the indirect questioning technique that I'll focus on for the remainder of the talk. So the list experiment is, again, an indirect questioning technique. And in particular, it's an experiment where the treatment effect is unbiased under certain assumptions for the true prevalence of the sensitive trait, so expectation of zi star. And to understand how this works, it's helpful to go through an example. So this is a study that was conducted by Collman, and Ericson. And they were interested in measuring the prevalence of workplace homophobia, but this list doesn't contain that item. So what they did was they ran an experiment. So they allocated their sample to treatment or control. In the control condition, they posed this list of questions. So I have more than one bathroom in my home. I can walk to a grocery store from my house less than 30 minutes. I can speak more than one language. All 4 of my grandparents were born in the United States. So these are a list of kind of hypothetically innocuous questions. And then respondents in the control condition are asked to fill in the bubble corresponding to the count, so not actually which items, but the count of control items that apply to them. Next, in the treatment condition, the respondents who are randomly allocated to receive treatment receive the same list of 4 items plus the sensitive item, which is I would be unhappy to have an openly lesbian, gay, or bisexual manager at work. And again, they're asked to fill in the bubble corresponding to the count, but not actually identify which of the items on the list actually apply to them. So again, hopefully people have an intuition about how this method provides respondents with greater privacy. but I'll kind of try to make it formal in the next couple of slides. So you can think of this list of 5 binary items as implicitly defining 10 categories that response can fall into. And this is a lot to throw onto the screen, but I'll walk through it. So on the left in blue, we have the individuals who have zi star equals 0. So these are the people for whom the sensitive item does not apply. So in this context, it's people who would not be unhappy with an openly LGB manager at work. And on the right in the orange is the set of people who would be unhappy with it. So this is the sensitive item. And each row here corresponds to a number of control items. So that's Y0I, a number of control items that apply to them. So for Y0I equals 1, for example, these are people for whom, for instance, they speak more than one language, but none of the other items on the list apply to them. And what the list experiment does is it kind of shuffles the respondents like this. So it's just kind of a slight clockwise rotation, corresponding to each of the possible responses, levels of the indirect response under treatment. So here, what's happened is that if someone answers 1 to the indirect response under treatment, we have a mixture distribution. Like, we're not sure whether they have the sensitive item or not, whether they have the sensitive item and no items on the list, or they don't have the sensitive item and 1 item on the list. And so what happens is that we've broken this identifiability aspect of direct questioning. It's no longer clear which group, conditional on them choosing one of the intermediate responses, which group the respondent belongs to. Now you'll notice that this identifiability aspect is still present in the floor and ceiling responses. So Y1I equals 0 perfectly reveals the truth, and Y1I equals 5 perfectly reveals the truth. And that's something that we'll talk about later on in the presentation. So my focus isn't on the list experiment, but I think it's helpful to go through the identification assumptions because we'll draw on them. We'll draw on them in the later parts of the talk. So these are just the assumptions that we need in order to generate our estimate of expectation zi star, so to identify the true population prevalence of the sensitive item. So first we need randomization of treatment, so ignorable treatment assignment, and intuitively we need this to ensure that the count of control items for the control group is unbiased for the count of control items in the treatment group. We need treatment to not affect the actual responses to the latent control items. So technically we need something a little bit weaker than this. So what this assumption says, so equation 2, it says that allocation to treatment or control doesn't affect the true latent response for any of the control items, when actually we just need the count of control items to be the same. But I find this kind of way of formulating it a little bit kind of more theoretically plausible or defensible. But here the idea is just that, that we need the count of control items to be the same for treatment and control. And then lastly, we need the no liars assumption, which just says that the answer to the sensitive item actually corresponds to a truthful answer, so a truthful indication of whether they have the sensitive item or not. And so intuitively, hopefully people have a good understanding of why the treatment effect in this case corresponds to an unbiased estimate of the true population prevalence of zi star, the sensitive trait. Okay, so that's the background for this paper, which again is titled Lying on Surveys. And as the title implies, the goal of this paper is to move beyond measurement of sensitive traits with list experiments. So beyond measuring zi star, to understanding who misreports, so who's responsible for discrepancies between DA and zi star. So intuitively, if there's a large difference between the responses under direct questioning and the list experiment, then there's evidence of misreporting. And so this is a question that's a kind of intrinsic theoretical interest. So again, in this paper by Collman, and Ericson, they were looking, one of the research questions motivating the study was, are Democrats or Republicans more likely to misreport homophobic attitudes? It also pops up in other papers as well. So this recent paper by Matt Nock and Garcia Sanchez asked this really fascinating question of, does territorial control by different armed groups in Colombia predict like preference falsification? So predict people falsifying their support for various armed groups. We also used a list experiment and direct questioning design for that. And the idea of this paper is that we can combine the estimates that we get from the list experiments with direct questioning to generate regression models of misreporting to try to understand who is responsible for generating, again, this misreporting. So I'm trying to make this a little bit more formal on this slide and talk about what the misreporting rate is and how we identify it using this combined design. So again, we're talking about situations where we have surveys where there's a direct questioning component and a list experiment. So by misreporting rate, what we want to estimate is the probability that conditional on someone having the sensitive trait, so conditional on zi star equals 1, that they falsify their report of that, right? So they provide a direct response of 0. So this, in this case, this is an underreporting rate, but we could imagine the converse would be an overreporting rate for other settings. We're going to make this monotonicity assumption, which basically means that the social desirability bias or the misreporting bias, in this case, only works in one direction. So conditional on not having the sensitive trait, no individual in the population falsely reports to having the sensitive trait. So this is also known as the no false confessions assumption. So there's no, so either underreporting is 0 or overreporting is 0. And then the rest of the argument goes as follows. So by Bayes' rule, we can rewrite what we want to estimate. So that's di equals 0, conditional on zi star equals 1. We can rewrite that as 1 minus the probability that they actually have the sensitive trait, given that they affirmatively answer the direct question, times the marginal probability that they affirmatively answer the direct question, divided by the probability that they have the sensitive trait. Well, we have all of these quantities. So the marginal probability that zi star equals 1 is given by the list experiment under the 3 identification assumptions that I mentioned previously. Under monotonicity, we have that the probability that someone actually has a sensitive trait conditional on them answering the direct question affirmatively equals 1. And then the marginal probability of an affirmative answer to the direct questioning is obviously given by the sample, can be estimated by the sample mean of the direct question. And so that's going to motivate this very simple ratio estimator of the underreporting rate, which is just 1 minus the ratio of the direct responses to the list experiment estimate. So to illustrate kind of, this in maybe a more intuitive way, we can imagine a population of unit length. So this gray bar here is the population. And the list experiment gives us orange box plus blue box. Oh, sorry, I didn't realize that chat would come. Sorry. I will go back. Okay. So we have, so the list experiment will give us orange box plus blue box. So that's the expectation of zi star. And the orange box here is the sample mean of the direct question. So under monotonicity, that's the group of individuals who truly have the sensitive trait and are willing to admit it. And so what we want to estimate is this blue rectangle here, which is the proportion of people who have the sensitive trait but are unwilling to admit it. And obviously that's just going to be the complement of the orange box, so expectation of di over orange box plus blue box, which is expectation of zi star. And that's going to be the quote unquote ratio estimator of the misreporting rate. Okay. So the next question, obviously, is, we don't want to stop there. So, for example, the earlier question was, does this propensity to misreport differ for Republicans and Democrats? And we could estimate that by just segmenting our sample into, these different strata depending on covariates, and then calculating this ratio estimator for each group. But that's going to have really high variance. It's not going to allow us to really identify small differences between groups. And so that's going to motivate a kind of regression modeling approach. And in the paper, I propose a couple different regression models, but for simplicity, I'll just focus on this maximum likelihood approach. And so here we're going to assume the standard kind of parametric model for list experiments that Kosuke and Graham and Kosuke worked on, and it's implemented in our software package list. And so here, the model is that the control response is followed by nominal distribution with the upper limit j and probability equal to f of xi. So that's a regression model. So xi here is the individual covariates. And f of xi parameterized by gamma. And the sensitive trait is going to follow Bernoulli distribution with probability equal to g of xi times delta. And we're going to augment this basic kind of maximum likelihood model with a probabilistic model for misreporting. So the probability of answering the direct question affirmatively, conditional on having the sensitive trait, is going to be Bernoulli with the probability 1 minus h of xi parameters by beta. And hopefully it should be clear that h of xi beta is a regression model for the propensity to misreport. So that's just the probability that someone falsely reports to not have the sensitive trait conditional on having it. For simplicity, I'm going to focus on what's called the partially overlapping design. So this is where the direct question is only posed to control respondents in the list experiment. And then we can think about the likelihood for these observations. So we're going to assume independence of di and y conditional on x. So conditional on observing di equals 1, the likelihood is g of xi times delta times 1 minus h of xi times beta, g of xi delta times 1 minus h of xi beta. And that obviously makes no sense to anybody, but recall that g of xi delta is the probability that the respondent has a sensitive trait. 1 minus h of xi beta is the probability that they're not shy about admitting that they have a sensitive trait, right? So conditional on observing an affirmative direct response, they have the sensitive trait under monotonicity and are not shy about revealing that. Conditional on seeing di equals 0, we have a mixture distribution between people who truly don't have the sensitive trait, so that's 1 minus g of xi delta, plus the fraction of people with a sensitive trait who are shy about admitting it, who misreport. And that's given by g of xi times delta, so the probability that they have a sensitive trait, times h of xi beta, which is the probability of misreporting that. And then we have the model for the control variables. And then for the treatment observations, this is just the standard maximum likelihood approach, maximum likelihood model for the treatment observations of list experiments. We don't change it here because we're only considering the partially overlapping design, and so we don't observe DI for the treated observations. But notice here that we have this same kind of mixture in equation 16, where there's uncertainty about whether anyone with an intermediate response on the levels of the response variable has the sensitive item or not. Okay, so because this is a methods talk, I'm just going to really quickly talk about how we estimate this model in case people are interested in using these techniques for their own work. So we use the EM algorithm, which is a helpful technique for estimating or maximizing likelihood models with mixtures in them. So the idea here is that we have these two mixture probabilities. So conditional on observing di equals 0 for the control observations, we don't know if that di equals 0 represents a truthful answer, so they actually don't have the sensitive trait, or if they have the sensitive trait but are unwilling to admit it. For the treated observations, we don't know conditional on observing yi equals y, where y is either not 0 or the maximal response plus 1. We don't know whether they actually have the sensitive trait and just have one fewer control items, or if they don't have the sensitive trait and have the exact number of control items that they report. And so the approach here is just going to be to assume that we actually observe the latent variable. So we observe the sensitive trait, write down the log likelihood that we wish we could solve, and then replace that latent variable with an expectation. So instead of actually observing zi star, we observe the expectation of zi star. And then in the expectation step, we're going to update that probability given the current parameter estimates. And then given those expectations, so it'll be a weighted average, we'll then maximize the log likelihood to update the parameter estimates. So that just looks like this. So assuming we observe ZI, we can break out, we can break out the two groups of respondents control respondents who answer DI equals 0. So if we actually observe, ZI star equals 1, then we know that they are the people with a sensitive trait but are obscuring it. Conversely, if we observe DI equals 0 and ZI star equals 0, then it's 1 minus G of Xi delta. So they actually don't have the sensitive trait. It's a similar process for the treatment observations. And then in the E step, we just update the probabilities. Okay, so that's very abstract, but we do it for a reason. So this is the application, again, the Collman-Ericson paper that I analyzed in this paper. And so again, they're interested in this sensitive item. So I would be unhappy to have an openly LGB manager at work. They use a partially overlapping design, meaning that only the control respondents answer the direct question. And again, they're interested, not just in how this kind of discomfort with the LGB manager varies in the population, but also how the propensity to misreport that varies in the population. Indeed, they find evidence of social desirability bias. So respondents are 67% more likely to express discomfort to agree with the statement under the list experiment. So that's 27% versus direct questioning. So that's only 16%. They kind of do a subgroup analysis where they look at the difference between the list experiment and the direct questioning across different subgroups. So they observe large differences in these differences for people who are more religious, so Christians versus the non-religious, and Republicans versus Democrats. But the problem is that they're doing this like on a kind of variable by variable basis. So first they just divide the sample into Christians and non-religious people, and then divide it in Republicans, Democrats. But these two variables, for example, are strongly correlated in their data, as you might expect. Right? So 70% of the response to their sample identifies Christian, compared to 30% of Democrats. Christianity is also strongly correlated with religiosity, which we might also think predicts the propensity to misreport. And Republicans, completing the triangle, Republicans also score about 1 standard deviation higher in the religiosity scale. So it's hard for us to disentangle, what's driving the misreporting bias. Is it partisanship? Is it religiosity? So on and so forth. And so this motivates a regression approach where we can kind of account for all these variables in the same regression. So again, we're interested in estimating the sensitive trait and how that varies as a function of responding characteristics. So that's G of Xi delta. We're also interested in modeling the propensity to report this. So that's H of Xi beta, just in the terminology. So I'm going to show two models, results from two models. So here are the coefficients for the three variables that I mentioned. So on the left, we have the model for the sensitive trait. And so higher here can be interpreted as a higher propensity as that variable increases, conditional on the other variables in the model, higher propensity to be upset by having an openly LGB manager. On the right, we have a model of misreporting. So higher here means that as that variable increases, conditional on the other variables of the model, that individual respondents are more likely to misreport. Negative here means that they're more willing to express that they actually have the sensitive trait, conditional on having it. So turning to the left-hand side first, we find that, I think, consistent with people's theoretical priors, that Republicans are more likely than Democrats and independents to be upset by having an openly LGB manager at work. For Christians, that point estimate is 0, so they don't, controlling for the other variables in the model, it doesn't seem like Christians are more likely than other religions to be upset by this. But it does increase with religiosity. So controlling for partisanship and the specific denomination, as people become more religious, they become more likely to be upset by having an openly LGB manager, purely correlational. So these kind of variables all kind of push in the same direction, but we find kind of interesting variation when we turn to the misreporting model. So this is, again, the model of conditional on being upset. How willing are you to admit that you would be upset? So we find that conditional on being Christian and conditional on religiosity, that Republicans are more likely than Democrats to misreport that they would be upset by having an openly LGBT manager. And again, this is consistent with the kind of very rough analysis that the original authors performed. But we actually find the opposite relationship with the religion variables. So in particular, so for example, as people become more religious, they're less likely to mask that they would be upset by having an openly LGBT manager. So that's the majority of the contribution. And just to kind of start wrapping up, I'll talk about some of the other contributions that the paper makes. So recall that this was the property of direct questioning that leads to misreporting. So it's the idea that conditional on observing a direct response, it's directly identifiable whether an individual has a sensitive trait or not. So also recall that under the list experiment, the floor and ceiling responses are directly analogous to direct questioning. So again, that's this kind of figure that we showed. So again, we have this kind of like, the floor and ceiling responses to the indirect response have the same kind of identifiability dynamic as direct questioning. And as a result, these floor and ceiling responses, so individuals who happen to have either none of the control items apply to them or happen to have all the control items apply to them, that also is potentially subject to misreporting and non-response. So just a very kind of extreme example of this comes from a list experiment that was conducted on support for the Taliban, where the researchers asked respondents the script, tell me how many of these groups you broadly support, meaning that you agree with the goals and policies of the group or individual. Again, don't tell me which ones you agree with, only tell me how many groups you broadly support. And you see in the control group, it looks fairly reasonable. There's a roughly uniform distribution across the levels of the response variable. But in the treatment group, we have these like very obvious floor and ceiling effects. So people, like no one in the treatment group gives the floor or ceiling response because the floor and ceiling response is analogous to direct questioning this way. It has this kind of identifiability property to it. And so the idea in the paper is that we can leverage this kind of analogy between the floor and ceiling responses to allow treatment respondents to be informative about misreporting, even in designs where they don't necessarily receive direct questioning. And so here, what we do is we just model the ceiling response as analogous to direct question. So if someone gives the ceiling response in this model, for example, they have the sensitive trait and are not shy about reporting it. So that's where the 1 minus h of x I beta is. And we just kind of modify the likelihood in this way, and it leads to, I show in the paper that it at times can yield potential efficiency gains, so smaller standard errors for the regression. And the reason is because we're leveraging this analogy to allow treatment respondents to be informative about misreporting, even when they don't actually receive the direct question. And then finally, the last part of the paper talks about 2A misreporting. So this is relaxing the monotonicity assumption. So again, this assumption is that the sensitive response, so like what counts as a sensitive response, is the same for all respondents in the sample. Yeah, so again, either the underreporting rate equals 0 or the overreporting rate equals 0. Like there's no one who kind of disagrees about what the sensitive answer is to a particular question. And we can like easily think of situations where this assumption is unrealistic. Like for example, the sampling frame includes people from very different like social milieus or people of very different ages. Like what counts as sensitive might be different for those individuals. And it turns out that in the fully overlapping design, so where we have direct questioning and the list experiment applied to all respondents, that we can actually identify and measure both the underreporting and the overreporting rate. And I won't go through the full proof. I know this is kind of a lot, but the key here is equation 28 here. So the key here is that we can stratify our sample based on their responses to the direct question in a fully overlapping design. So we can divide the population, so we can divide our sample into whether they answer the direct question affirmatively or not. And then the list experiment estimate within that strata will let us identify the probability that Zi star equals 1 conditional on Di equals 1. And then through Bayes' rule and various manipulations, we can pull out in this case, the underreporting rate. So we can get Di equals 0 conditional on Zi star equals 1. And then by the same argument, we can also identify the overreporting rate. So the probability that Di equals 1 conditional on Zi star equals 0. And in the paper, I talk about some situations where this might be realistic, and I show how to also use regression to model both under and over reporting. So just to wrap up, so the concluding remark is list experiments are a useful and very popular technique for reducing bias from misreporting and non-response. That said, statistical analysis of the list experiment can be really tricky, and often there's a very sharp kind of bias variance trade-off. So we can estimate these things in the aggregate, but often we want to kind of apply some structure to the problem and do regression in order to reduce the variance of list experiments. So the maximum likelihood approach models can be really sensitive to modeling assumptions. But by combining list experiments with direct questioning, we can improve both aspects. We can improve aspects of both list experiments and direct questioning. So intuitively, by combining list experiments with direct questioning, we can try to reduce the variance of list experiments while at the same time accounting for the bias of direct questioning. And as a nice side benefit, we can generate these multivariate regression models of misreporting. Okay, I'll conclude there.
All right. Excuse me. All right. Thank you, Winston, for that presentation. At this point, Winston Chou is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window. And during the talk, a question came in, which I will ask now, from Thomas Ball. It's clear that these approaches will generate a likelihood, but what about uncertainty? For example, earlier approaches in the 1980s to eliciting responses to sensitive questions produced estimates for the first moment, but other moments, such as the variance, were infinite or undefined. What's the case with the method you're describing?
So the variance estimation is going to be contingent on the particular modeling approach that we use. So if we use just the difference in means to estimate the aggregate prevalence, then we can use the difference in mean. We can use kind of standard variance estimation techniques. If we use, for example, a more complex maximum likelihood model, then we also use it's based on the curvature of the likelihood function at the optimum. So the more kind of structure that we put on the problem, so the more assumptions that we make about the parametric distribution of the variable, the lower that variance will be. So that's one answer to the question. The other way of answering is that we can think of two sources of maybe not variance but error, and there it's hard because we don't actually know the true value of the parameter that we're trying to approximate. So we can think of two types of error. One is modeling error or sampling error, and then the other error is the systematic error of the method, in this case, the list experiment. And there we have to address that using validation studies to see if if the method is actually good at eliciting the true prevalence of the sensitive trait.
Sort of a related question to that one. You can think of the variance, for example, of the propensity to misreport, or the variance in the prevalence of a trait, especially if the trait is not just 1, 0, but if it's a scale. You can imagine that variance being an interesting parameter in and of itself, sort of like a Garch type model, where the essentially you could say, well, there's a distribution of the characteristic in the population, and the degree to which there's variation in the population is actually itself of interest. In other words, how much internal disagreement is there inside of that subgroup. So is there any way that you could extend your approach to actually model the variance of again, this works better if it's a continuous characteristic other than because a discrete characteristic, the variance is fixed or is known. It's just a simple function. But for a continuous characteristic, that could be. Is there any way of studying the sort of the variance in a subpopulation of that?
So I'm really not sure if there have been any applications where the estimand is continuous or like not, 1-0 basically.
Right.
And kind of trying to think about ways you could adapt this to try to measure a continuous variable or even an ordinal variable. I guess you could maybe have a version you could discretize it by like doing above or below a certain number on the scale. But that's an interesting question. I'm not so. I should definitely say that the parametric assumptions that we make at the very least definitely assume that the sensitive trait is binary. It's an interesting question.
Yeah, I'm thinking of so you mentioned support for the Coliman, right? That's obviously a 1-0. But if I were, suppose I just forget about the fact that people don't want to tell me that. You could easily imagine there being a latent utility characteristic for how enthusiastically I support the Coliman,
right? And
that there's a cutoff in that,
and the shape of the distribution, like if it's like a horseshoe versus so there are kind of latent utility approaches to eliciting sensitive traits. So like the endorsement experiment is one, and then also the implicit association test, I believe, also has a kind of latent utility type of thing where they. But I wonder also for this approach is I'm fairly sure that they make some kind of assumption about the shape of the latent variable. So you wouldn't actually be able to estimate, for example, different kind of parametric shapes. But yeah, that's interesting. Although I guess in the example of like the horseshoe or the bimodal, like this kind of discretization would work well.
So I have a question. I guess it's sort of a methods question, sort of a substantive question. I'm interested in the study of misreporting as its own. So you said it mentioned it as a side benefit, right? That's your last bullet point on the slide.
Yeah.
And I'm thinking about what about that as my prime, dependent variable or estimand of interest. So I was hoping you could talk a little bit about the substantive importance of that, how it could be used, as sort of ideas you have about how to take these models and study misreporting as a phenomenon in and of itself.
Yeah, so I realized a little too late that I think this concluding remarks slide is for a different presentation. But yeah, so the focus of the paper is very much on generating these models of misreporting as a something in its own interest, and obviously the kind of replications and the applications. Those are studies that were actually trying to look at misreporting as something of substantive interest. I think so. I mean, it's domain specific. So obviously there are different questions that this question is important to different subfields from a substantive perspective for reasons that are in the inherent to the subfields. But kind of one area that I'm interested in pushing a little further on is looking at the setting of like expressive responding, or what's being called in the literature like partisan cheerleading. So this is basically responding where there's very obvious differences in what counts as kind of the sensitive trait. So in the paper, I have this example where I study a list experiment that was conducted among far-right voters in Germany. And so these are voters with kind of they come from very different cultural milieus and have different social norms. And what we find there is that there's actually over-reporting of the party line, which in this case is anti-refugee sentiment. So for most people, we would expect that what counts as sensitive in that context is actually having anti-refugee sentiments. But it's different if you are a supporter of an anti-refugee party, because there you feel it's pressure to kind of toe the party line and to express ideas that are congruent with those of your party. And so this is an example where you'd expect there to be this kind of two-way misreporting dynamic. And so indeed, when we apply the method, we find evidence of that. And that's something that I'm interested in applying further, is looking at, kind of how, because, partisanship we think is this variable that not only changes, what you believe, but also what you think you should believe in a way, like the kind of ideals and norms that you should live up to. I think it's still very nascent.
I mean, one thing I was thinking about is dynamics in misreporting over time. So in my relatively short lifetime, I think I've witnessed a pretty significant change in how people think about the sensitivity of certain opinions related to gay and lesbian rights, for example, gay marriage or gay adoption by gay couples. And one thing I thought of as, well, that's interesting. Maybe if I had older survey data versus newer survey data, if I had a panel, for example, where they were asking that question over and over, and I had direct questioning and a list experiment, at least for some subpopulations. I probably don't have it in the larger population. I could actually measure over time how the propensity to misreport changed in a sort of panel setting, which I guess would require, so that requires the misreporting model to change over time, right?
Yeah, that's right. So there are two. So I guess I have three thoughts. One is, very, just an approximation of this is looking at how misreporting varies by age, and that's in the model too
right.
for this the homophobia one, and we see kind of interesting dynamics there, but obviously that's confounded with the
right. Cohort, age, and period are all
right. The other thing is that we have to take into account also the changing denominator here. So the misreporting, at least as I think about it, is conditional on having this homophobic preference or this socially undesirable preference, the propensity to report that. Well, over time, that denominator also is going down, and so it's unclear whether the social desirability bias is going down, or whether just the group of people who feel that bias is shrinking. And so I know that there's been work on this question of how does the willingness to express a homophobic attitude vary by partisanship? And I think originally the hypothesis was that Democratic people would feel it much more intensely because the nature of their party and so on and so forth. But we don't see that in these data, and I think that's in part because the base is smaller for Democrats. Like the group of Democrats who actually feel this, attitude is very small, and so the confidence intervals for the misreporting rate for that group are very wide.
I mean, if you think about going back, I realize a lot of the data actually come from a shorter time span. But if you imagine going back to like the 1960s, the 1950s, the bias would actually go in the other direction, right? You would go from having a case where people were afraid to express support for these things, to a total turnover where now I suspect that people are more afraid of expressing opposition to those things, and so the direction of the bias can even change.
I see what you're saying.
Yeah.
Right. So that can be accommodated. I mean, you're right that in the kind of the monotonicity assumption would change, and so the estimator that we have for that would change.
Right.
But a more flexible estimator that allows for both, both directions in a panel setting could actually work pretty well, and that would be really interesting.
What I'm basically thinking is, the people's sensitivity to a question is a measure of something. It's a measure of social desirability, and you can sort of pull that out of it over time.
Yeah, and so that could vary across partisanship, that could vary across time, that could vary across space. So an example is, I have a paper, and some colleagues did a list experiment in Mississippi on an anti-abortion referendum. So, and there, what was socially desirable is very different than what we might think it would be elsewhere. Like the socially desirable response is actually to say that you would vote for the anti-abortion referendum, whereas in different settings you could imagine that's switching. And so having the ability to kind of model this non-monotonic social desirability bias or whatever bias is important.
Seeing no more questions, I'm going to go ahead and end the IMC. So I want to thank Winston Chou for being our presenter this week. I want to mention that his presentation will be posted to our website shortly after this broadcast. If you'd like to share this presentation with a colleague or watch it again later, I'd also like to advertise the next talk in our series. Join us on February 15th, when we will host Aaron Rossiter from Washington University in St. Louis for a talk. Check out our website, www.methods-colloquium.com, to get more information about that talk. Winston, thanks for being our presenter today.
Thank you.
All right, and I hope to see everyone next time.